Before we start, let me warn you, today's topic is so weird that if I said it casually in a grocery store, someone would call security. Imagine, just imagine, you throw a tennis ball at a wall. You expect it to bounce back, right? But instead, it passes straight through the wall. No hole, no cracks. It just poof appears on the other side. Sounds impossible? Welcome to my lecture series of learning quantum computing from zero to hero. I am Professor Janki Bhimani, and on day-to-day basis I help invested stakeholders to make the most out of their resources by inventing novel solutions using emerging tech, from modern storage systems to quantum computing and machine learning, all while tackling the real-world challenge of real system deployment. Basically, I live at the intersection of science, creativity, and practicality. Now let's talk something fun. Quantum. Well, it is impossible to pass through a wall if you are a tennis ball. But let me tell you, if you are an electron, proton, a Cooper pair, passing through walls is just another Tuesday. Welcome to the world of quantum tunneling, the phenomena behind nearly every quantum device on Earth today, from IBM to Google to Rigetti. And this year's 2025 Nobel Prize in Physics went to three scientists who didn't just study this effect. They tamed it, measured it, controlled it, and built devices you can literally hold in your hands and where quantum tunneling happens on a macroscopic scale. Ladies and gentlemen, meet our superheroes, John Clark, Michel Devoret, and John Martinis. Let's begin. These three scientists didn't wait for electrons to behave on their own. No, they said, electrons, sit, stay, tunnel. Good boy. What they built is basically a tiny superconducting sandwich. Superconductor, ultra-thin insulator, and superconductor. And inside this sandwich, electrons don't just travel, they moonwalk through barriers. Their devices let them pass current, shine microwaves, measure voltage, watch tunneling happen in real time. And their experiments laid the foundation for modern qubit. Before we get there, we need to peel back 100 years of quantum history. Let's go time traveling. In 1911, Heikki Karmali-Aunts, possibly the only man who loved cold more than ice cream vendors, cooled mercury down to a few Kelvin. As the temperature dropped, something incredible happened. Resistance dropped to zero. Zero, not 2% off, not discounted, absolute zero. Electricity could flow forever without losing any energy. Basically, this would be the only place where you never receive electricity bill. Wouldn't that be wonderful? This was the birth of superconductivity, a new magical state of matter. But nobody knew why it happened. Then later, actually electrons normally repel each other, just like siblings fighting for a last slice of pizza. But Leon Cooper, around 1956 to 1957, proposed something disturbing. Electrons can pair up. Yes, electrons forming couples. This happens because As one electron moves, it pulls the positively charged lattice slightly. Another electron is attracted to that distortion. Boom! Cooper pair. Remember the word Cooper pair. Two fermions become one boson. If you don't know what fermions and bosons are, stay with me. They love sharing. Bosons, they love sharing. Fermions, they hate sharing. They pile into the same quantum state, like students crowding the only charging port in the class. You all are bosons. This led to the famous BCS theory in 1957. Now enters Brian Josephson, a 22-year-old young man. Not even done paying his university library fines, he proposed, if you place a superconductor, insulator, superconductor, Cooper pairs, remember the Cooper pairs that were formed when electrons paired up to become boson? These Cooper pairs will tunnel through insulator from one superconductor to another superconductor, like tunnel through insulator, pass through. Everyone else said, dude, that literally what an insulator doesn't allow. An insulator doesn't allow to pass through. While Josephson answered, classical physics doesn't get to sit at the big boys table here because quantum particles behave like waves and waves love leaking through barriers. This became Josephson Junction, earning him the Nobel Prize. Little did this young 22-year-old boy know this would one day be the heart of quantum computers. Quantum tunneling is the reason behind how flash memory, the one which is within your SSDs, they work. If you don't know what SSDs are, I have another whole lecture series on storage systems. Watch that to learn more about them. Further, quantum systems are the reason behind radioactive decay. Scanning tunneling microscope sees atoms. The sun shines. The qubit existing in quantum computers. Without tunneling, nothing would function, not even your mobile phone. So next time your phone freezes, blame everything except tunneling. Before we return to 2025 Nobel Prize experiment, we must understand some basic concepts such as quantum tunneling, BEC, which stands for Bose-Einstein condensate, and superconductivity. Let's break them down in Vimani style one by one. First, quantum tunneling. Most people explain quantum tunneling by using tennis ball and wall analogy, which we started with. But that is flawed. It's not the right way of thinking it. It is as flawed as thinking a friend who says they will be there in 5 minutes will actually be there in 5 minutes. If you have such a friend, you know what I'm talking about. Coming back to quantum, a better analogy would rather be you roll a ball towards a hill. If it has enough energy, if you would have rolled it with enough energy, it goes over, right? If not, it comes back always. But in quantum world, even if the ball doesn't have enough energy, sometimes it appears on the other side without climbing the hill, as if a magical tunnel opened inside. Real experiments show this with electrons in a vacuum tube encountering electric barriers. Classical rule, no energy, no crossing. Quantum rule, let's roll a dice and see what happens. Bose-Einstein condensate, BEC, that's our next concept. particles are sorted into two big families, fermions and bosons. Fermions are particles that hate sharing. This consists of particles such as electrons, protons, neutrons. On the other hand, bosons are particles that love sharing. These are particles such as photons, gluons, and Higgs. Bosons can all enter the same state. They become one giant quantum blob. Even fermions can become bosons if paired, like electrons forming Cooper pairs, or atoms like helium-4 where particles pair up and behaves as a collective bosonic object. Cool them enough and they enter BeC, a fifth state of matter. Helium-4 even climbs walls and escape containers, just like what you do with your responsibilities on weekend. I know it. Next, that brings us to understanding superconductivity. In superconductor, electrons pair into Cooper pairs. Cooper pairs behave like bosons. All enter one quantum state. They flow with zero resistance. It's like a traffic jam where all the cars decide to act like one giant bus and suddenly everything moves smoothly. This sets the stage for the Josephson effect. Cooper pair tunnel through an insulator even when classical physics seem to be challenged to explain it. Now we return to 2025 Nobel Prize winners, Clark, Devoret, and Martinez. They built a current-biased Josephson junction, placed it in a copper tube, cooled it to a millikelvin, and observed microscopic quantum tunneling and discrete quantum energy levels in a circuit. What is each one of it? So microscopic quantum tunneling is observing the quantum tunneling effect, which we discussed earlier, not with tiny particles or not with just one Cooper pair, but the collective phase of millions of electrons tunnel out of energy well altogether. So that's macroscopic quantum tunneling. This is like watching an entire football stadium teleport together. That's big, right? The second thing, discrete quantum energy levels in a circuit. What does that mean? So inside the washboard potential, the system has quantized energy levels, states that can be excited with microwaves, transitions exactly matching quantum predictions. They even did resonant activation, gently nudging the system with microwaves to make it pop into different energy state. This was the first time, basically, a microscopic object obeyed quantum rules. A circuit behaved like a quantum particle. Tunneling happened in a measurable, controllable way. Boom! Nobel Prize. Two energy states inside the junction, stable, controllable. That was the beginning of what we call as superconducting qubit today. Superconducting qubit is the base of many quantum computers around us, including IBM Quantum, Google Sycamore, Rigetti, Amazon Bracket, and most major quantum processors. Martini later led Google's team to quantum supremacy in 2019. Devoret continued advancing quantum hardware. Clark trained generations of scientists who now lead the field. Their work literally powers the quantum computers you can run on cloud today. This brings us to the end. Can you tell quantum tunneling was first theoretically explained by which physicist? He was also Nobel Prize winner. One hint, he also made significant contributions to the Big Bang theory. Not the series, the actual theory. I will see you in the next Simply Learn Qubit. Goodbye. Take care until then.